this one is not difficult. So what is that here is we have a heat exchanger, heat exchanger, and temperature outside whatever we call it is TW, and liquid flows in at velocity should be u0. We know the velocity, it has Cp. The area for this is A. The diameter is R, radius, and the velocity, the fluid has a density rho, and the heat transfer coefficient is at H. So all these things we know about it, but we just express. We don't have value for them, but we know about this. And so firstly, if we want to solve a heat balance or the equation for this, first we consider about heat balance equation. This one doesn't like the previous ones we just talked about, because the previous one, there's no fluid move, and what we get there is just pure heat conduction. But here we have fluid motion, so we need to take that into consideration. And in that way, because, let me see, he didn't mention to saying, I'm not quite sure whether he stated here, but definitely he stated in class that the heat conduction is ignored in this problem, because if you are considering it's the fluid that carries the heat flowing through, rather than the fluid stays still and the heat diffused goes through by conduction. So basically, we are considering about the overall this type of thing. So for this type,
do we need to look up like some number, like Pythagorean number or something?
no, because basically this one, there's no number given here. Totally no number, so very easy to see. No.
Yeah.
So what we consider here is the heat comes in, still the heat comes in minus heat goes out should equal to accumulation. But here we said it's a steady state, so all the things become to the heat loss. Let me consider what comes in. Let's still take this x minus x plus delta x, for example. In that way, heat comes in is the heat stored in the fluid itself. So let's say it comes in at Cp T in minus T, let's say, reference. The heat goes out at Cp T in plus, let's say, T, I say here is Tx, and here is Tx plus delta x minus T reference. And when we consider about m, because the fluid here is in motion, so m becomes to rho a u, and similar for this m becomes to rho a u. Then this is heat in, this is heat out. The difference between them becomes to Cp rho a u times Tx minus Tr minus Tx plus delta x plus Tr. So the reference temperature disappears, and what we left here, becomes to Tx minus Tx plus delta x.
T, the u is velocity, right?
Yeah.
Velocity.
Yeah.
And will the velocity change?
No, I think it's steady.
Oh.
It's steady, so whatever it's steady. But so this is the left-hand side. And we are saying about this is when we are consider is in a finite width element with length of delta x. And then we consider about the heat loss. For heat loss, we need to apply the Newton's law for each point when we are considering, because we are here we're considering 1D system. So for each x, there's a heat loss which equals to h times 2 pi r h a times t minus tw. So what I mean here is for, say here is x and here is x plus delta x, and for each x we have a heat loss which equals to this. So basically for this distance it becomes to this. And if you are considering a certain distance, this one equals to this one. But then we don't want to consider its integration. We want to consider at each point to make it more accurate or something. We differentiate for both sides. And this one becomes to h2 pi r t minus tw here. And here you get this, when you're doing the differentiation, it becomes, let me see, it becomes 2 minus partial t over partial x. Let me see. Heat loss. Yeah.
And that's partial t over partial x or partial t?
Partial t over partial x. Initially we have here for the delta t, right?
Yeah.
And then we differentiate. Then it comes to, so you consider this to be for each, so delta t over delta x, right? And when delta x becomes too very, 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 very small, it becomes 2 partial t over partial x. Let me see. We can write, sorry, dt over dx, because this is, we don't consider time variance here, so it's only one variable. And if you consider about the sign positive or negative, I usually, I know, ignore the sign. This equation must equals to that equation. And here, because t is higher than T1, it's losing heat. So this one must be a positive one. And as it goes, the temperature drops. So this sign must be a negative sign. And because this equals to this, so you have to have a negative sign before. I'm not good at analyzing dt over dx, how this itself. I'm good at, okay, here's the equation. There should be a negative sign. And then what you can do is you can just divide both sides by Cp rho AU, and then get here is what he considered this as lambda. And you put that back, you will get dt over dx plus lambda t minus tw comes to 0.
So lambda is that whole.
Yeah, 2 pi RH over AU naught rho Cp.
Okay.
Yeah, that's a lazy. What then we get is that we only have, this is, it's quite easy to solve, and we have plenty of, it's relatively easy to solve. So I say dt over dx equals to minus lambda t minus tw. And if you put that back this way, it becomes 2 minus TW over dt equals to minus lambda times dx. So it's the third time today we met this type of formula. And the answer for this becomes to t minus t w becomes to a to e to the minus x. And then we would like to solve for t, for a. Then we put our initial boundary here is, as it says, the fluid inlet temperature is T naught. So we know T naught minus TW equals to A. That's one inlet here, x comes to 0, so that's A, because here e to the power of 0. And then A becomes to this, so T minus TW equals to T naught minus TW times e to the minus lambda x.
So is that where you put in just boundary conditions? Or
Yeah, initial condition.
Initial conditions.
Let's see, x equals to 1, x equals 0, t equals to T naught. And basically that's the final answer for the question. And then the question asks you to draw the general profile for the temperature. What you can see is here you get T equals to TW plus whatever T naught minus TW times e to the minus lambda x. So apparently it should go like, here is TW. Initially you have T equals to T naught, and then it goes something like I, but you will never reach this line. Because here it's get an exponential decay, and this one is just a value. The question then asks you to say, what happens if you increase the volumetric flow rate? Well, we say lambda equals to 2 pi RH, 2 pi RH, rho Cp U naught. What happens if you increase volumetric flow rate? So basically when you are increasing volumetric flow rate, that means if everything else is constant, means your velocity will increase. Q increase, velocity will increase, so lambda will fall down. So initially, when, for example, it's here 1 minus 100 or minus something, then it becomes 2 minus 200. So the curve here should really goes slowly. Let's say slowly. It should, let me see.
Be quickly, no. Let me see. Smaller. I think it should be.
Lambda decreases.
Quicker, right? Yeah. So because initially you have minus,
Temperature reduces.
yeah, 100x, now you have, for example, you have 1, now you have 100x. So the impact of x on the equation becomes bigger. So which means the x, initially you need x here to have the same of x smaller here. So which means you have
Yeah.
this one. And the second question asks, what if you increase the diameter but keeping the volumetric flow rate constant? So the things related with diameter is U naught here, A here, and R here. So I say lambda is proportional to R over U naught times A. And U naught is a function of volumetric flow rate. It becomes to R over volumetric flow rate over A times A. So basically, A cancels with each other. Because the question said this is constant, but R is increased. So if R increase while Q is constant, lambda will increase. So it will goes like this way. You see? No, sorry, I think I made it wrong.
Let me calculate.
No. If lambda decrease, so it becomes e to the power of. This is original, and for this question you got e to the minus 1, and this one you got minus 200. So I think I make it wrong.
If you increase it, it will be high. If you decrease the lambda, that will be higher than the, for example, e to the minus.
So this will be this this answer.
Yeah.
Yeah, this always happens. When we are recording everything and we find out that's wrong. Like them just struggling
So
with the
the
process.
for the the highest one, that is the lambda is the smallest, right?
Yeah. Smaller lambda, the
Increase.
curve goes
Up.
upward.
Yeah.
Okay, finish.
Cool.
Yeah. Finish. Hey, are you happy today?
Yeah,
Yes.
that's good.
Yeah. Thank
Thank you.
thank
Very